All right, so let's go ahead and look at some of the information necessary to work on the module folder 4B pre-lab for Ohm's law. Simulation once more, preloaded in another tab. Not as many instructions this time to get us started. A couple of things that you may already know or you might have to look up and check and see. So first question is, what kinds of batteries are 1.5 volts? Well, we can kind of spoil it. If you look at these, they each say 1.5 volts and they look like your disposable type, C or D batteries maybe, because they're kind of wide comparatively. For obvious reasons, there's no brand name on there, but it looks like a common type of battery. If we think about some of the other things, car batteries are usually 12 volts. The little square batteries, like little rectangular batteries, is probably a better description, are the 9-volt ones. Big square batteries, which sometimes you find in small, like vehicles for children, are 6 volts, or sometimes those are used for like cameras and things that are left out in the woods or whatever that are going to last for a while. So there's, voltage doesn't necessarily have anything to do with size. That's something I also want you to think about for this lesson. A 9-volt battery, the little thing that sometimes goes in remotes and toys, is 9 volts, and it's smaller than the 6-volt batteries that might go in a Barbie Jeep. So, but anyway, most disposable batteries like AA, AAA, C, and D, most of those are 1.5 volts. Okay, then going on to the next one, if I wanted to make 9 volts, how many batteries would I have to make? So I suppose the question 2 kind of spoils the first one, but that's okay. It can't be perfect. I can actually bring the voltage up, break it down. So if you had trouble figuring out, how many batteries make a certain number of volts, and for reasonable numbers at least, we can check and see. So I've turned this up to 9, which is the maximum, and you can see 1, 2, 3, 4, 5, 6 of these. Okay, and then I want to find the resistance that's going to cause a certain amount of current with a 9-volt battery. So if I had a 9-volt battery, would work the same as these 6 1.5-volt batteries that are in series. They're all touching in a line. So, it just would simplify the picture, I suppose, if I had an actual 9-volt battery. Okay, and I want to make 0.0455 amps, which may seem like it's a much smaller number than what's here, but you need to remember and pay attention to this and remember what it means, I suppose. But this is milliamps, all right? So milliamps are 1,000th of an amp. Think milli like millennium, right? It has something to do with 1,000. So here, milliamp is 1,000th of an amp. So if we convert this to milliamps, we're going to multiply by 1,000 and bump the decimal 3 times. So that's going to turn into 45.5. So it's actually more current than what was originally on here. So I want this to go to 45.5. Now, unfortunately, the answers can be very slightly different depending on your simulation and your device and your screen resolution and possibly your zoom and a few other factors. But we can get pretty close, and then our numbers should still obviously be the closest ones to whatever the answer choices are. Okay. What I want you to think about, though, is resistance and what that word means just in general. Resistance is going to make something harder, right? So resistance essentially makes it harder for electricity to flow. So if I were to up the resistance, so notice that this represented here by filling in with more black dots, I guess more things to be in your way if you want to think about it like that. And so my current is actually dropping. I went from 18 down to 9. So it's not what I wanted to do. I think it makes sense, and if you think about it, I think you'll agree that I want a lower resistance if I want more current. I want it to be easier for current to flow. So notice as I drop this down, there are fewer black dots to be in the way. There's bigger arrows showing current, and then even up here, my eye is getting bigger. Then I want 45.5. So I might not be able to do perfectly. Yeah, it's not going to work, but I can get reasonably close. So notice I wanted 45.5. I can only get to 45.9, like said, different from different devices, but 196 ohms is really only close to these two. So think about it. I had a little bit more current than I was really looking for. So I need a little bit more resistance to scale that down very slightly. So I want an answer it's a little bit above 196 ohms. And so 198 makes the most sense. So yeah, unfortunately we couldn't get a perfect match there, but it's still logically the closest one. Okay, and so let's say I want to make 6 volts. Again, remember that each AA battery is 1.5 volts. You might be able to do the mental math. It's not necessary though, because we can take and scale this to 6 volts and then, count, right? 1, 2, 3, 4. Same as doing 6.0 divided by 1.5, we get 4. There we go. Be careful not to fall for the obvious trap. A lot of people see this and then just pick 6, right? But we want to make sure that we're paying attention to how many batteries it would take, and they're 1.5 each. Okay, so we want to find the resistance that's going to make 12.0 milliamps. So that is measured in milliamps, just like this is. I want only 12 though, and right now the way this is set, I have 30. So if I want my current to come down, remember I need it to be harder for the electricity to flow, so I need more resistance. And then maybe, pretty close. I can't quite get the exact answer. I get 2 spots here that round close enough to be 12.0. I had 498 and 501, so it should hopefully not be too much of a stretch to say that that's 500 ohms. Okay. So next question, how many batteries do we need? So this time we don't know the potential. We don't know the voltage that we're going to need to make this work. We want 0.006 amps. So remember this is back to full, just the A, full amps. So multiplying this by 1,000 will get us milliamps. And so we want 6 milliamps with a resistance of 500. Well, I can't get perfect, but that's as close as I can get. Now I want this to say 6 milliamps. So let's think about what the potential, the voltage would do. So think about potential as the ability to do something, right? So we're going to look at this as like the ability to push current around in a circuit. Well, if I want to have less current, then I need to have less potential. I need to be pushing less, right? So if this goes smaller, and again, think of it as not a perfect analogy, but it's good enough that I want to have less pushing of current, right? So notice that my resistance didn't change. It's still the same 501, but I was able to lower my current by lowering my voltage. Okay, so be careful with this one again. 3 is an answer choice, and 3 volts is what we're looking at here, but it says how many batteries? Right? So 1, 2, 2 batteries. Okay, then a few more to finish up here. It says we're going to stay at the default 4.5. I'm going to refresh here just so I get rid of some of the weird numbers that popped up. So 4.5 volts, again, that's 1, 2, 3 disposable batteries, or I guess potentially rechargeable batteries if we're being environmentally friendly. I want to know, how do we get more current? So if I'm going to leave the voltage alone, how do we get more current? Okay, so the thing that I'm changing is my resistance. You can also think about this formula directly. Ohm's law says that V equals I times R. So if I'm looking at I in particular, then I want this R to move away. So we can divide and move it. And so I is equal to V over R. So if you look at the R, the thing we're changing, it has an inverse relationship here. It's on the bottom of some fraction that we're using to solve for something, which means that changing that value is going to change the answer in the opposite way. If I make R bigger, I'm going to get less current. If I make R smaller, I'm going to get more current. So let's read the question and then check it and see if it works. If I want to get more current, again, then I want my resistance to do the opposite thing. So let's see if getting less resistance gives us more current. feel like we tried this earlier. Seems like it's working just fine. In fact, now the eye is so big it doesn't fit on the screen. Here, I'll get the arrow to fit too. Okay, so less resistance made more current. It's easier for current to flow around, so overall more of it does. Makes sense to me. 8 is basically a maximizing type question. Can we make the current in this setup 1 amp? So remember, 1 amp is 1,000 milliamps, right? So can we make this, say, 1,000? Well, minimal resistance is going to get us most of the way there, right? We're already at 450, which is almost half of the number we're looking for. If I lower my voltage, notice that that's going in the wrong direction, right? I have less potential, basically less um, work from the battery pushing this around. So I want a bigger number. I is off the charts huge. We can't even really tell that used to be a letter or that these were arrows. Just seems like a bunch of weird shapes. But notice that in my most extreme cases, the biggest number I can get is 900. And then even if somehow we did that wrong, if we maximize and minimize, go in each direction, we can't ever get anything bigger than 900 milliamps. So no. Even if you weren't sure, please go with the 50-50 yes on this, yes or no. Not probably nothing explodes. Like just pick one, but hopefully you'll be able to tell. All right, and then last two, and they kind of go with each other. And actually, we just did one of these. So one of them's asking, what we give the maximum value for current? Well, we know the maximum value of current in this setup is 900 milliamps. So let's see, what do we do to get there, right? Voltage is capped. R is sank all the way down to the bottom. So let's see if one of our answer choices says that. This is maximum voltage, but then it also says maximum resistance. So be careful with this. Well, maximum voltage and minimum resistance. So essentially, you want the highest ability to push around electrons and the least resistance working against you when you're pushing those electrons around. Okay, then technically we also saw number 10 earlier, but if you read it carefully, you should be able to figure out that it's the opposite of number 9. So if I wanted to get a minimum value, smallest possible answer, then I need the opposite of what's here. So I can get 0.1 milliamp, a portion of a milliamp, which is already a portion of an amp. So very, very small here. I think that's as small as we can go, right? Because naively you might think, okay, we want everything to be little, but as it turns out, that's just not true. Okay, so look at where our positions are. Voltage is down, resistance is up. So voltage is down, the minimum resistance, or sorry, minimum voltage and maximum resistance. Seems like that one. This one technically said minimum voltage at the end, but it was minimum resistance, which is not what we had. All right, that should be it.